Okay, so in our previous class, our target is the flow velocity field. So today we move the topic to accelerations. So as I highlight two sentences, the predicting force is important to engineer designers. And because the forces are related to the acceleration, so when we have the engineering problem, so we take a look for the force, and the most important parameter is the acceleration. So as the example, first we need to know the acceleration factors for our questions. So you see the slide showing here, we have the object. He puts the object here, and far away from the object, we will have the free flow. So we will have a free flow to the right. Okay, so when the straight line much closer to the object, when the straight line much closer to the object, so we know that the velocity in here, should be higher, right? Then the velocity in here is the rho. Because the straight line is much closer to the object, so the flow velocity will decrease when the flow straight line moves to the right. So in that case, we know that the accelerations, A, the factor, should be have the factor direction to the left. Because the particle, the flow velocity move to the right, the velocity will start from the high to the low. So, but we actually know the velocity, even though decrease, but the flow factor of the velocity is go into the right. Okay, so sometimes we will have the problems. We put the object on some fluid environment. Like the example showing here, we have the free flow far away from the object. So we need to take account with the direction of the acceleration and the direction of the velocity. Okay, so this is just what we need to consider before we find the solution for the problems. Okay, and the previous slide, the example, the flow always linear flow, but sometimes our flow, straight line or path line showing here, should be the curvature curve. So like the example showing here, the straight line, also we can say that is the path line are curvatures. So if the straight line is curvature, so the acceleration direction we can distinguish, divide it into two parts. So first part is the accelerations. The acceleration is the tangent directions of the path line. So in that direction, we call that the unit factor is the UT, is the tangent directions. And related to acceleration, we call that the AT accelerations. So we actually know that the tangent acceleration will be the effect for how large the speed. So the tangent acceleration will change the speed, magnitude of the flow velocity. So how about the effect of the normal? We call that the normal accelerations. So the normal acceleration usually is associated with the change in velocity directions. The change in flow velocity directions. Okay, so if the straight line or path line are not linear, it's the curvatures, and then we practically we have the two accelerations. We call that the one is tangent directions, another one is the normal directions. And then the tangent direction change the magnitude of the velocity, but the normal direction change the flow directions. Okay. So what's the problems usually we meet? So we start from the functions are showing here. The velocity vectors will equal to the v, and then the direction is the tangent directions of the velocity. Okay, so the idea is we have the velocity vector, and the vectors has the ut directions. As I mentioned, the velocity direction is the tangent of the straight line, right? You pick up the one point and plot the tangent line. It is the velocity vectors at this point. So we know that the magnitudes of the velocity should be a function of the straight line point. And at a different time, maybe we have a different velocity. Okay, so the velocity speed is as a function of the straight line point and the time. The different straight line point, we have different velocity speed. Okay, but we focus on the tangent unit vectors. So as we know, how can we compute the acceleration vector? We can directly compute the acceleration vectors with partial v vectors dt, right? The partial v vectors dt. And then we can distinguish two parts. The first part we differential with the velocity speed, a scalar divided the time, and we keep the unit vectors of the ut. We keep the unit vector of the ut. And the second items, we keep the velocity scalar, but we take a differential of the unit vectors of the tangent directions. Okay, so we have the two parts. We have the two parts we need to take into account. The first one is, how about the differential velocity scalars with the time? So we need to first we need to differential for this. Try to find the answer for the differential velocity scalar of the time. So as we know that the v is as functions of the straight line point and the time, and we differential with the time difference, right? Because the v scalar, velocity scalar, has two variables. And the first variable is the straight line point s, and the second variable is time. So we need to partial differential for these vectors, parameter. So the first we partial differential, we just dv, we partial differential with the ds, right? And then ds will also change with the time. Okay. And the second partial differential, we just focus on, we directly differential with the time. Okay, so we have two variables. One variable is a spatial parameter s, and another variable is the time parameters. So we partial differential both two parameters. Okay, and if you take a look, these items, ds dt, ds divided dt, that indicates the streamline point change with the time. The streamline point change with the time. So this item is equal to the v velocity, right? Because the differential point change with the time. Streamline point change with the time. So this is also the v. So we can rewrite the equation will equal to the v and the dv ds. And the second item we keep it is a dv dt. Okay, so these items we are looking for the acceleration items for the tangent unit factors. So our second purpose, how about the differentials? The differential with the time for the unit factor tangent. The differential with the time for the unit factor tangent. So we need to consider the condition difference is we are looking for the differential is the target is the tangent unit factors with the time, right? So we may consider how about the problem. So I plot the string line. I plot the one string line. This is the blue line is our string line, and I pick out the 2 points. Maybe 1 point in here, and the second point in here. And I know the point I plot in here, and I take the tangent. I take the tangent line. So this is my tangent line at this point. And another tangent line, maybe like this shape. Okay, and the 2 black line in here, we can say that this is the ut unit factors, the tangent factor at this time point. And then maybe the delta t time point pass. So the unit factor of the tangents change to this direction, and I plus the delta t time. So the delta t time pass, so the unit factor of the tangent change the directions. Okay, so what's the problem? We have the we can consider the problem now. Move to the delta ut factors, and then we know that the delta ut factor at a different time point is the ut factors t plus delta t minus the ut factors t, right? This is a unit factors changed when time increase delta t. Okay, so I move but how the result if we take the difference? How about the result? So I move the line ut. This is the maybe this is the line for the ut factors. The line for the ut factors. Okay, so the ut factors at the time plus delta t minus the ut factors. So the directions, the factor minus together. So the final result factor maybe will like this direction, right? The ut factors at the t plus delta t minus the ut factors. So we'll change the factor direction at these directions. So if I move the blue line factors to here, so you can consider these directions is equal to the normal factor directions. This directions is equal to the normal factor directions. So we know that the direction will change to the normal vector directions, right? The two different time UT unit vectors minus the direction will change to the normal directions. So that's why I write down the normal direction here. And how about the length, the vector length of the blue line in here? So how about the arrow? So as we know that the theta may be changed in here is the delta theta, right? The theta change in here. And if I know the length, in here, I can multiply the length by the delta theta to compute the arrow length in here. So the length in here for the unit vector, we know that the arrow will equal to the unit vector's scalar is equal to 1, right? Because the UT unit vector is a unit vector. So the length is 1. Multiply the delta t will equal to the arrow length. So we put and we know that the unit vector, the absolute value is 1. So the arrow will equal to delta theta. So we put the delta theta, because here is the arrow multiplied with the normal unit vector directions. So finally we know that the delta UT vectors will equal to the delta theta, and but the factor will change to the normal factors. Okay, so we go back to see, this is our final purpose. We would like to calculate the differential unit vectors with the time. So the next step, we should compute the delta UT vector divided the delta t, right? And then we know that the upper is the delta theta unit vectors, but for the normal directions, divided the delta t. And we know that the delta theta divided delta t is the angular velocity. So we have the angular velocity omega in here, and we still have the unit vector for the normal component. And we know that so maybe I just take a note. This is the angular velocity. And we know that the angular velocity will equal to the velocity divided the radius, right? The velocity divided the radius, the rotate radius. And so finally, this is our result. And then we know that if the delta t time is close to small, so the delta UT vector delta t will equal differential UT vector dt, right? Okay, so that's our basic ideas. Okay, so and you right now, what are the answer you have? The first one, you already know the dv dt, these items, and you already know the d unit vector tangent directions dt. So you actually know the answer in here. So we have this item. Okay, we have this item. So we put all of we know, go back to define the acceleration factor again. So we summarize all of the answer in here. The A acceleration factors and the answer in here. So we know that the V, dV, ds, and the plus the dV, dt And this item is only for the unit tangent vectors. And the second, the normal, the acceleration related to the associated with the normal directions is this item. And the additional v in here. So it will equal to the v squared divided r, but the direction is the normal vector directions. Okay, so finally, our acceleration vectors we can distinguish, divided into the three parts. The two components, but with the three parts. The first component is the tangent components, but with the first item in here, we call that is the convective accelerations. And the second item with the time, we call that the local accelerations. But the second directions is the normal directions. And then we call that the acceleration is the centripetal directions, accelerations. Okay, so the first item, convective, because this is related to the convective behavior. This is acceleration is associated with the convective behavior. And that is a local, and the final one is the centripetal accelerations. Okay, so for me and you, we need to remember the final formulas for the acceleration factors. Okay, so the following slide, we have some exercise, and then you can see how can we apply the acceleration factor equations to find out the answer. So the first one, this is a nozzle. So we have a nozzle and designed such that the velocity in nozzle varies as the where the velocity u0 is the entrance velocity. So we have the velocity go inside with the velocity u0. So we have the u0 is the 10 meter seconds. And the velocity functions defined in here. And the directions is x directions. Okay, and the L is the length of the nozzle. So we have the L in here. Okay, so what's the problem? And the problem tells us the length in here is equal to 0.5 meters. And we know that the velocity in here is the uniform cross each section. So please find the acceleration. Please find the accelerations at the halfway through the nozzles. So where the point we need to meet. So we have the point in here because the question tells us is the halfway. So the point in here, how about the acceleration in this point? How about the acceleration at this point? So we need to take into account. So the length in here is the L divided 2. Okay, so we go back to see our acceleration factor showing here. So we have the acceleration factor. And first, you see the functions. It is our function, right? And this velocity function didn't change with the time. So that indicates the flow is a steady flow. If the flow is steady flow, so we don't have the items contribute from the local acceleration because the velocity didn't change with the time. It is the steady flow. And the second, because we know that the velocity in here is uniform. It's a uniform flow. That indicates the flow straight line and the path line is not the curvature line. If the line is linear line, straight line, so that means we don't have the normal directions acceleration. So we don't need to calculate the normal accelerations because we don't have a radius, right? The line, straight line is straight line, not the curvature. Okay, so we only need to calculate the acceleration for the convective accelerations. Okay, and we know that the S, the straight line direction right now is along the x directions. So our A acceleration along the x, and so the V only have the x direction velocity. So we have the U and the du dx, right? Because all of the parameters with the same directions along the x. Okay, so we can first we can compute the U and the x. The U x is at the L divided the 2 at the black dot in here. So we have the velocity function is U 0 and multiply the 1 minus the 0.5. Right now the x is the 2 over L, right? And divided the L. So we divided the L over 1. And this is the first. We can calculate the U velocity at the point x equal to 2 over L. So you can see the L can cancel out. And then we know the U0 is the 10 meter per second. And multiply the 1 minus the 0.5 divided the 2 over 1. And then the unit in here, this is no dimensional. Okay, so we use the calculator to compute the answers. So the answers around the 13.33 meter per second. Okay, so we already find out the answer for the U in here. So our second topic is how about the du dx, right? So the second we need to calculate the du dx. So the du dx, so we need to calculate the differential for the velocity functions. So the U0 is the constant, so I take it outside. And we do the differential for the velocity function. So I keep the, it is the I may take it much clearer. So the dx and the U in here is the U0 multiply the 1 minus the 0.5 x divided L, and this is the minus 1. Okay, and then you do the differential along the x directions. So U is the constant. So I just take the outside, and we have the minus 1. Okay, we have the minus 1, and the differential in here is 1 minus 0.5 x and L, and to be the minus 2, right? And there are some constants values with the x. So we have the minus 5, 0.5 divided L, right? So this is our differentials if you calculate by yourself. Okay, so I just noticed that for this item, because there is a constant values for the AKs, so that's why we have these items. That's why we have this item. So we just put the number inside. So what do we have? We have the 10 meter per second velocity, and this is -1. This is the minus. So the minus cancel out, and the inside in here, we have the 1 minus the 0.5, and the x is 0.5 L in here. This is our x. Also, and you put the x inside, and then there is still the 0.5, and the upper is the -2. It's a -2, and the L. What is the L in here? The L in here is 0.5. So in here is multiply 1. Okay. So so right now you can just use your calculator to compute the answers for our final velocity numbers. So I use my calculator calculate the answer. Okay, wait a moment. Okay, so this is some variable difference. I check the answers. So the x and the divided L 0.5. Again, I use the calculator. 0.5 multiply 0.5. Okay, and the 0.2. So in here, difference. So we have 0.5, and the x is the 2 over L, and the divided the L, right? So in here, this is yes, is 0.5 divided also multiple. Yeah, it's correct. Okay. So 0.5 multiply 0.5 and 1 minus, and have the square. Answer is a square, and the 10 divided this square. So the answer is equal to the 17.77 around. Okay, so and then you can combine all of the parameters together, because you already have the du dx in here, and you have the u answers. So finally, we know that the ax is equal to 13.33 multiplied by 17.77. Okay, and then sorry, the unit in here, this is because we divided the x dimensional. So in here, the unit is the s over 1. It's a s over 1. So we know that the final unit in here is s squared over meters. Okay, so you can check the answer by yourself, and the answer is around the 236.97. Okay, and it's similar to the answer we write down in here. Okay, so this is just a very quick exercise. You just take a look what the answer you need to support. And then sometimes we don't need to calculate all of the items, such as this is a local acceleration, because the flow is steady flow. So we don't need to take into account. And then we know that the uniform flow, so the flow is straight line. So we don't have the curvature, so we don't need to have the centripetal accelerations. Okay, so and this is a second exercise. Again, we take the problem, the look first, and then you see we know that the velocity in the nozzle is linear. It's a linear nozzles, and we have the base and we have the tips. So we find out the boundary. This is the base, the nozzle base, and this is the tips. This is the tips. And assume the flow is the dimensional flow. That indicate also is a linear straight line, not the curvature. So for these questions, we only need to consider the acceleration along the tangent directions. Okay, so the problem is, what is the convective accelerations, the middle way between the base and the tip? So the point what we are interested in is in here, because it's a midway. And we know that the velocity at the base, in here is the 1 ft per second. And the tip velocity is 6 ft per second. Okay? And the nozzle length in here, the L, is equal to 25 inch. The 25 inch. So we already know what the velocity acceleration we want is a convective velocity. Okay, so the A should be equal to, and we define along this direction is the AX. Okay, so it's a convective velocity is U multiply the du dx. Okay. So we need to compute the u at this point, and the du dx. How can we compute? Okay, so first I change the unit. L is the 25 inch. So I convert the unit to the ft. So the foot is divided the 12 will to be the ft. So the 25 divided the 12, so it's equal to the 2.083 ft. And the half length, this is the half length, so it is the L divided the 2. So we know that the L divided the 2 again will equal to the 1.0416 ft. Okay, so first we can compute the du dx first, because we know that the tip velocity is 6 ft per second, and the base velocity is 1. So I minus 1, and how the distance changes? The distance changes start from here to here, so equal to L, and we know that the L is equal to the 2.083 ft, right? So we can compute the answer is equal to around it's about the 2.4. And the unit is second over 1. So we have the velocity differentials. And what are the u? The u, because we have the u base, right? And we know that the gradient of the du dx, and the multiply the length is 2 over L. And we can compute the u at the dot location in here. So the u base, we know that the u base is the 1 ft per second, and the plus the gradient is 2.4, and the 2 over L, we know that the length is the 1 0.0417 ft. So the unit in here also the ft per seconds. Okay, so we know that the U velocity 1.0417 multiplied the 2.4 and the plus 1. So the velocity in here is 3.5 ft per seconds. So we can summarize that we have the delta U delta x and we have the U velocity. So right now we have all of parameter we need to compute the convective acceleration. So the U 3.5 ft divided s and multiply du dx is the 2.4 and the unit is the second over 1. Okay, so we can know the final answers is the 8.4 ft divided the second square. Okay, so the idea is quite simple. Just based on your velocity field, and you can consider how kind of the acceleration you have and include in your problems. So for these problems, we actually know the question. We can directly to compute the convective acceleration. So we don't worry, we don't need to calculate others. But sometimes the question just tell you you need to compute the acceleration. They don't assign the acceleration is convective, local, or centripetal acceleration. So you need to calculate all of the acceleration you will have and include in your problem. Okay, so this is one example, and directly tell you you need to answer the question is convective accelerations. Okay, so we move to the next topic is the Euler's equation. So it is our second important equation in our class. The first one we have teach is the hydrostatic. So the second equation in here, we call that the Euler's equations. So how different they are compared to the hydrostatic. Okay, so we may just write down some ideas. So as you can see, this is a fluid object in here. And we know that we have the flow start from the left to the right. And along these directions, we call that the directions is arrow directions. It's arrow directions. So to the right is positive factors and the left is negative. And we actually know we under some assumptions. So the first one assumptions, one, we consider the condition is the implicit flow. So that means there is no viscosity effect. No viscosity, we don't have the shear stress, right? So in our problem, we only have the pressure force. We don't have the shear force. Okay, so no shear force effect. And the viscosity force are 0. That indicated the implicit flow, right? So usually our liquid material is water, and the water viscosity, dynamic viscosity is quite smaller. So it's satisfied for the water liquid. And the second conditions, we assume the particle is accelerating. The particle is accelerating. And the final very important conditions, the constant density assumptions. So we know that the flow should be the incompressible flow, right? Because incompressible flow satisfy the liquid density always constant. Okay, so based on the Euler's equation, we have two assumptions. If I use the flow condition to describe, the first assumption, the flow is invisible flow. The second assumption is the flow is incompressible flow. Okay, two assumptions. We know that there is no shear stress, and the liquid has the constant density. Okay, so we only have the two assumptions, and then we can consider how the problems, and we put the final formula in here. This is the formula indicate the Euler's equation, and what's the PZ in here? PD is the piezometric pressure. The piezometric pressure is equal to the pressures plus the gamma Z, right? The pressure plus the gamma Z. And usually we call that is elevation pressures. And this is the absolute pressures. And this is the piezometric pressures. And we know that the gradient, piezometric pressure gradient. So we have the gradient operator in here is equal to the fluid density multiply the accelerations. And there are additional minus symbol in here. It's again, when we tell you the hydrostatic equation, we know that the pressure difference will equal to the gamma, right? The pressure difference will equal to the gamma. But in that condition, we still have the minus symbol. That indicates the elevation increase and the pressure decrease. If the elevation increase and the pressure decrease. So again, in here, the same. If the piezometric pressure gradient increase, and then the acceleration will decrease. Okay, so that's we have the minus. So the idea is, because the accelerating is in here, right? The positive directions, because we know that this is accelerating conditions. Okay, so and the second, we know that in here is a high pressures, and the right hand side is the lower pressures. Usually the higher pressure will flow to the lower pressure, right? Okay, so that you know that the pressure increase gradient is these directions. So the pressure gradient is the opposite direction compared to the accelerating directions. So that's why we have the minus symbol in here. The pressure will increase to the left, but the acceleration will increase to the right. So that's we have the negative symbol in here. Okay, so here maybe I stopped in here, and the next class I just derive and prove the Euler's equation. OK， 好，那这里其实蛮重要的，就是这是我们这堂课的第二个很重要的方程式。那等一下我们就要来推导怎么样得到右下角的这个答案。那你可以去跟之前的流体静压方程去比较，那它们之间有什么差异？那我们这一堂课因为多了一个加速度，以前我们在流体静力的时候是不可以有加速度的。如果流体会移动，是呈等速运动，要么它就不移动。哦，那今天开始就变成是流体开始移动，而且在加速，不是呈等速哦。之前我们是等速嘛，所以它是静态静力学这样子。那我们现在变动力学以后，运动学就开始东西要开始有加速度这样子。那我们下一堂课再好好解释一下。